In the last video, we took a look at how to do vector addition, subtraction, and multiplication by a scalar using components. And in this video, in our quest to start doing kinematics in 2 dimensions, we're going to revisit the definitions of velocity and acceleration and see where that takes us. So the general definition of velocity is exactly the same. It's still the change in position with respect to time, or we can say this is the displacement with respect to time. Nothing has changed other than now we put little vector signs over everything. And similarly, we'll define the acceleration of something to be the time rate of change of its velocity. And remember, these triple equal signs mean by definition. So let's just go and take a look real quick. We can revisit, say, the a car that was picking up speed from a traffic light. So here we can go ahead and figure out, let's take a look at figuring out, using these definitions to figure out our velocity and our acceleration. So let's say we want to know the velocity in this time interval here. We'll call this interval 1. This interval here, we'll call this interval 2. And we'll just go ahead, put our origin right here. We can say stick it over here. So then we'll say that the position of the car here is R1. The position of the car here is R2. And the position of the car here is R3. So again, just a quick reminder here. We can measure position from any convenient origin. It doesn't matter which. So if I want to know the average velocity over interval 1, we can first go ahead and calculate what was the change in velocity over interval 1. So change in position. So delta R here would be R2 minus R1. We can go ahead and do this graphically. So there's my R2. I will add to that a negative R1 to get delta R. We'll say delta R1 here because this is time interval 1. So then we can conclude that the velocity points to the right. Oops, let me change the color. The velocity points to the right and it is proportionate. So V1, let's say. All right, then we can play the same game here with R3, time interval 2. We can say that delta R2 would be R3 minus R2. So then we'll be taking my R3 like that, adding to it negative R2 like that to get an R2, delta R2. That's longer than my original delta R1. Looks like maybe double. So in that case, my velocity will have to point twice as long in the same direction. So now to find the acceleration, we can say, all right, the acceleration is the change in velocity over time. So that will be my v2 minus my v1 over delta t. All right. So then there's my v2. I will add to that negative v1 to get delta v pointing to the right. So then we conclude that my acceleration points to the right. There we go. And we've seen this before. So if all that's happening is speed is changing, if the speed is increasing, the acceleration will point in the same direction as velocity. And if the speed is decreasing, it'll point in the opposite direction of the velocity. Well, that's all well and good, but now let's say you are moving at some constant speed around a circle. Here, you might at first blush think that you're not going to be accelerating, but you would be incorrect on that, and here's why. So let's say this is the circle you're moving around. There, let's put it out there. Let's go and mark off 3 positions, and I will just go ahead and use, use the center as the origin. All right. So let's say this is, let's make a straight line. So we'll say this is position R1. Then sometime later, position R2. And equal amount of time later, these should all be equal angles, position R3. Okay. Let's redraw that R2. That's looking a little sketch. There we go. That's better. So again, I would like to find what the acceleration is. But to that end, I need 2 velocities. So I'll need to find velocity in the middle of this interval and the middle of that interval. So we can find that. So let's go do it for this one right here. We can say delta V equals delta R1, we'll say, be equal to my final position R2 minus my initial position R1. All right, so we can draw in my R2 like so. Then we will add to that negative R1 to get my delta R1 like so. So that means that my velocity at some point in the middle of the interval will have to point in the same direction. I'll call that V1. And it turns out that that point will be right in the dead center of the interval. So V1. And notice that it's tangent to the curve. This will always be the case. The velocity will always be tangent to the curve. To prove that, uses the methods of calculus. So I'll dispense with that here. But the velocity, but you can, I think you can intuit that at least over small intervals, the velocity should be tangent to the curve. And because it always is, I can draw another one here. Again, tangent to the curve, trying to keep it the same length. There we go, something like, oops, had it. Third time's a charm, right? Yeah, I'll do. So there's my V2, also tangent to the curve. So now if I want to find my acceleration, I can go back to the definition. Say that acceleration is the change in velocity over time. So the change in velocity would be my V2 minus V1 over time. So the time will always be positive, so it's just a matter of finding my V2 minus my V1. So let's do that. So here's my V2, like so, and I will subtract from it V1, so this will be my negative V1, about like so, to give me a delta V. It's going to do something like that. So then that means that the acceleration is pointed in the same direction. So this would again be at the middle of the interval, so it'd be at this location right here. What we end up getting is the acceleration points into the center of the curve if you are going at a constant speed. Now, in general, the acceleration can point any which way. But what we get out of this is that the parallel components of acceleration are associated with a change in speed, and the perpendicular components of acceleration are associated with a change in direction. All right. So with that, in the next one, we'll get numerical about this and look at objects flying through the air. Have a good one.